FHWA Intro Logo. Saxton Laboratory Intro Logo. Cooperative Driving Automation CDA Collaborative Pilot Test 1. In spring 2023, the Federal Highway Administration, also known as FHWA, completed a distributed collaborative test called Pilot 1, using prototype elements of the Virtual Open Innovation Collaborative Environment for Safety, or VOICES test platform. Pilot 1 was a collaboration between FHWA, the University of California, Los Angeles, or UCLA, Econolite, and Nissan. For the first time in the history of surface transportation, government, industry, and academia co-simulated surface transportation technologies in a distributed virtual research environment. Pilot 1 demonstrated capability to safely test vehicle and infrastructure system-level interoperability using diverse models in an eco-driving application at an intersection. It also collected data to inform the draft SAE International Standard on Assured Green Period. Each of the 4 test sequences incrementally added complexity to the scenario and introduced each of the test partners gradually into the co-simulation environment. All the components of Pilot 1 were simulated and hosted by the participating test facilities: FHWA's Turner Fairbank Highway Research Center in McLean, Virginia, Nissan in Farmington Hill, Michigan, Econolite in Maumee, Ohio, and UCLA in Los Angeles, California. All these sites used the Cars Learning to Act, or CARLA, simulation environment for the tests, but each site brought its own models into the simulation. FHWA and UCLA sites each ran a simulated automated driving platform. FHWA site ran a Karma platform vehicle, and UCLA site ran an Open Cooperative Driving Automation, or Open CDA vehicle. Nissan site ran a kinematic vehicle model. Econolite ran a copy of their internally developed virtual traffic signal controller. All parties ran the test sequences on the generic CARLA map Town 4, except for the last, most complex test sequence, which ran on a digital twin of a real Los Angeles intersection provided by UCLA. Throughout each test sequence, the vehicle's basic safety messages, or BSMs, and the virtual traffic signal controller's signal phase and timing, or SPAT, messages were broadcasted and recorded. Pilot 1 started with Nissan running a kinematic vehicle model approaching an Econolite-run signalized intersection model at 5 predetermined speeds and starting distances. Nissan and Econolite were able to collect data for research and development on the SAE Assured Green Period standard and to lay the groundwork for future, more extensive collaborative tests. The next test sequence increased the complexity of the vehicle infrastructure interaction. UCLA's vehicle accelerated towards the same Econolite-run signalized intersection. This time, the vehicle adjusted its trajectory to stop at the light based on the SPAT information. It then proceeded through the intersection once the signal changed to green. The third test sequence expanded on this by adding another vehicle running simultaneously. The UCLA vehicle again accelerated towards the Econolite-run signalized intersection, but this time, Nissan ran a vehicle in the crossing direction. The UCLA vehicle used the Econolite SPAT information to safely adjust its trajectory to stop at the red light, while Nissan's vehicle passed through its light. The UCLA vehicle traveled through the intersection when its signal turned green. The last, most complex sequence introduced potential vehicle conflict and added simulated perception-based vehicle controls. FHWA's and UCLA's vehicles traveled in the same lane and direction towards the Econolite-run signalized intersection at 30 kilometers per hour. The UCLA vehicle followed using simulated visual perception to detect the Karma vehicle in front of it and avoid collisions while traveling. Future work could explore deconfliction strategies and how other vehicles' behaviors impact planned energy savings. By testing together in this shared virtual space on a secure network, each organization was able to advance their collective capabilities while achieving various individual objectives, including interoperability testing of models before wider release, identifying conflict scenarios to refine algorithms, safely conducting tests at a much faster rate than traditionally possible, more effectively integrating currently disparate infrastructure and vehicle systems, accelerating standards development, and cultivating the future workforce. Such testing enables organizations to easily leverage each other's capabilities rather than develop everything in-house, and reduces barriers to innovation in connected transportation. For more information on CDA collaborative testing, please visit the Federal Highway Administration's website at www.fhwa.dot.gov. FHWA Outro Logo. www.fhwa.dot.gov and social media icons. The U.S. government does not endorse products or manufacturers. Trademarks or manufacturers' names appear in this video because they are considered essential to the objective of the video. They are included for informational purposes only and are not intended to reflect a preference, approval, or endorsement of any one product or entity.